Hey, oh, so hey, sorry, I forgot to remove the layer, and I also answer about the lights. Yeah, I hate these lights, but I'm not in my current or my regular, I won't say, setup. But hey, I'm so glad I got the chance to be in this Global Hack Week. I know it's the last day. I know some of you thought that you won't be seeing me in this Global Hack Week. The thing is, I was very busy, actually. I was doing the defense of my thesis. It was on Monday. And yesterday, the light made me feel you're under a spotlight. Yeah, it's actually a direct spotlight. I think it's the stream. No, I don't like this lighting. Also, it makes my big forehead looks even bigger. So yeah, okay, it's a vanity thing. I admit it, but I don't like the lighting. But I know if I turn it down, I am not visible, uh, and I think it will be better with this. What was your test about? That's a great question. Actually, let me start answering these questions. Cannot wait to learn and create an IoT project that throws eggs and unexpected bypassers. I don't know. That sounds fun in theory, but hey, think about the poor people that will be receiving the eggs. Uh, Yay, howdy, IoT time. Yes, and like make me feel like you're okay. Now, perfect. The what was your thesis about? That's the real world project I want to showcase. I'm going to tell you all about my thesis project. And I didn't build it out, by myself. I mean, not alone. I was with a team of four, including me. Um, so this was a huge project that took me around 2 years of my life. Everything was fine. The result is that I'm an engineer now, so I'm very happy about this. Um, but yeah, I almost missed the chance to give this session to you because also I was preparing for my defense, and yesterday my nephew was born. So a lot of things happen in July for me. Also, at the end of the month, I'll be moving. But hey, I'm alive. And there's a lot of things happening, but I am really, really happy about being here and being able to share this with you. I know there are plenty streams that happened before that were amazing, that were really cool. I was trying to keep an eye on them too. Also, we got the introduction of the mascot. If you didn't see it, remember you can always watch the recordings of the streams. And well, let's start with this. The people with the axe thrown will be pineapple pizza lovers. They deserve it. Okay, I kind of agree with you. They do earn it. Super excited to learn about this awesome, cool project. Hey, thank you. So, let me start breaking this down. First, I want to show you in this part one all the theory, and we are going to be taking a look to the code, like in deep, because there's a lot of code. I have to admit it. Even though it's a mechatronics engineering project, which also required a lot of circuits, a lot of mechanics, and a lot of control theory, it has a lot of coding because, well, I'm a little bit biased to the software, right? So, um, but in this part one, I will show you the repository. In the repository, we're going to take a look to all the work done. Actually, I am going to share my slides, and I have to apologize because these slides are in Spanish, because I do present that in Spanish. But don't worry, I'll be teaching them in English, so you can understand what's happening there. And there's a lot of, how to say it, um, there's a lot of images, so the text in Spanish, it's actually a little bit. So let me start sharing my screen, and I had prepared a second monitor. Oh, this is not displaying. I was going to use my iPad as a second monitor to be taking a look to the stream and also be sharing my thoughts and the code and everything, but I don't know what happened. My iPad doesn't connect to the sidecar as it should, so I have to apologize about that also. Um, so give me a second, and I'll be ready to share this. Also, stay hydrated because it's a heat wave here in Mexico, and it's super bad weather. In the morning, I was kind of freezing. Later, I was very warm, and now I am all freezing again. So, um, yeah. Sorry. Here I have it. Let me present it. Oh yeah, I'm not sharing the screen. Give me a second. Okay, you should see this now. This is the stream, of course. But I can come here now, and this is the slides. Yeah, we did it on Canva because we didn't have that much time to prepare the presentation. But I have to admit, I kind of like it, and it fits the aesthetic of the UI that we will watch later, right? So the topic, it's about a system for um, making acoustic treatment of a room, an audio room, moving acoustic panels, right? That will be the translation. The automate system for doing acoustic treatment in acoustic audio rooms with the movement of acoustic panels. So, introduction, just to make it short, it's that we require to upgrade the regular acoustic treatment. In the past, and in this image you can see it, you probably in an acoustic room you can see a lot of panels that have different shapes and forms and they are made of different materials, but they're all stick in the walls, right? Um, the problem is that these panels, these materials, help us modify the acoustic of a room, but it's static. And if we want to change it, will do it via software, right? We proposed a system that that enhances this treatment by doing that automatically, right? So that's why our objective is to automate the process of acoustic treatment of the room, right? Any questions this far? Okay, no. Remember, if you have any question, just put it here in the comments. I'll be jumping in and back to see and try to resolve it. So that's the introduction, that's our main goals, and then let's take a look on how we do it. We divided in 5 models. They are not in order, not by the number, but they are in order for you to understand better. The first model, it's the modifier of the acoustic, and you can think of this as the muscle of the IoT project, because this is the one that takes the panels, and we made these panels in wood, and then we add a layer. Well, the base is in wood, and then we add a layer for each panel face, one being reflective, one being absorbed, absorb. Yeah, that will be the word. I'm not sure about that. it absorbs the sound waves, right? And the other one diffracts them, so it makes them go not just in one direction, but in many directions. That's the main idea of those three phases of the panels, right? And in our initial design, we try to move them using a system that has a crown and endless what's the word for this in English? Well, and an endless movement system, and another system that makes the panel fit or unfit this movement. So that's how we can stop them. That was the initial approach. Then, due to manufacturing reasons and trying to give less maintenance to the project, we reduce it to just having one crown with the endless movement, and then applying and giving the other panels movement via bands, right? Um, so these B bands introduce us a problem that the movement was asynchronous. We needed to be synchronous, and we uh, tried to correct them using another coupling system, but the problem was that that slightly change in the synchronicity of the movement break the entire system. Then we tried another approach, which was directly applying a motor to each panel. Now, once we had the panels made, we can make more analysis on them, and we discovered that it was a gear motor available that was big enough uh, in terms of the force it generates to break the initial uh, the initial movement required to move the panels. So yeah, this in general, it's the body or the muscle of the project, right? Uh, this was the mechanical part, as you can see. This far, we already introduced a little bit of the motors and, well, not directly, but implicitly the circuits behind it. But this was that part, right? Then we have to, this is an acoustic project. This was an implementation of mechatronics engineering, so we needed to have the business logic part, let's say it that way. So we need a model to generate and measure the acoustics. Let me see, I'll be stepping each model to see if you have any questions. Okay, no questions yet. Perfect. So basically what this model does, it's that in what's the word for that also? Weird question. Well, we play an audio that's an excitation file. That excitation file that's playing in yeah, the audio. It's a sound sweep. What does sound sweep means? It looks like that graphic, like this one here. It means it's a sinusoidal audio that goes from small frequencies to high frequencies. So it's like a pitching tone, right? And then we record how that audio it's interpreted by the room. So how the room responds to that audio, it's uh, the other file we care about. So this far we have these two files. The one we play that's already existing, and how the audio responds to that file. That's the other part. And then we have another thing that's the impulse response. And the impulse response, if you don't know, as me at the beginning of the project, what is in audio, it's an important file or an important measure to know the characteristics of the acoustic in the room. How we get this impulse file, it's that we turn these first two files, the excitation file and the response file, into an impulse response doing an inverse convolution, right? That's a mathematical thing. You don't have to worry about that. And then we apply a filter. In this filter, it's about signal processing. We want to get rid of the bands of frequency that are out of our business need. And in this case, we have a big spectrum of the frequencies we want to analyze. So we just left behind the ones that are less than 88 hertz and the ones that are higher than 5657 hertz. And then we got our impulse response. Then for processing, and this is for us as the software developers or the ones that we want to care about more, or we are going to, how to say it, develop the connections, the more interesting one. I mean, don't get me wrong, the first two were really important, and also if you're going to be doing IoT projects, you have to, well, that not only in IoT, I have to admit it, it's all engineering, right? It's really difficult that you are going to be doing a just engineering project. You have to apply engineering in something for the real world. So in this case, my real world project was acoustics. In yours could be, I don't know, agronomy. So you have to learn a lot about agronomy, right? You will have to learn if you want to make an IoT project for growing, I don't know, tomatoes. Which are the variables you have to measure? You have to measure humidity. You have to measure, I don't know, the time that the plant receives the sun, I don't know, lumens, those kind of things, right? That are out of the scope that you normally do. But you have to be really, really aware of what's happening. And another great advice I can give you, and that happens to us with this project, it's that don't try to automate one thing that you haven't mastered doing manually. So that said, let's continue with the processing model. Um, oh, you have questions now. I know it's in Spanish, but we'll be getting access to the slides. Yeah, actually, I'll download the PDF and I can share to you later. Yeah, thanks for the recommendation. Oh, actually, in the repository I will share, they're already there, so don't worry. Um, we will check the repository. Just let me go through the slides and we can start checking in the code, right? Thank you. This is so cool. I want to watch this show, but I have to be forced by some friends to have a sleep schedule. Okay, yeah, it's kind of late here, so I'll head out to sleep. It was so great to see you. Okay, this call has converted. Thank you so much. Remember, you can always watch the recording, and thanks for the interest. I'm so happy to share. In what language are the slides? I can understand it. They're in Spanish. Because I'm a Spanish native speaker and I didn't have time to prepare them in English. I'm so sorry about that, but don't worry, all the code and all the other things are going to be in English. And I'm trying to explain what's happening there in English as well. And in the slides, there are a lot of images, so don't worry about that. Bye 404. Bye. Perfect. So let's continue with the explanation of the processing model. In the processing model, we do have the interactions from the system. So we have 1, 2, 3, 4, 5 main actors here. The first one is the interface, the UI, the web page where the user interacts with the rest of the system. We have a server that makes the connection to the database, that handles the data. We have a lot of things to process. Heavy processing actually happens here. Also, I do did for the audio processing a Python one that's kind of living here instead of doing another server. Hey, don't judge me. It was a weird thing, but I was under pressure for the times. So I will show you what I mean in this part. But just don't judge me and trust me. This was kind of hard to get, and I didn't have the time to connect to different pieces of software. Well, and also these two at the same time connects to a thing called the broker, and the broker handles that communication to their devices. So this is where the IoT starts making sense. We have developed the code for connecting via a protocol that's called MQTT, message queue telemetry, telemetry, something like that. Actually, let me Google like really quick. What was the meaning? Message queuing telemetry transport. I was missing a T. Yeah, transport. Um, that lives inside these Node MCU developing boards. If you don't know what the Node MCU developer boards looks like this. These are these ones. And why these ones, you may wonder? Well, these boards have the special feature that already come with an ISP chip. This specifically one has an ISP12E, but there's also the ISP8262 or something like that, the 32 from All Life. Um, and that allows the board to connect to Wi-Fi, and with that we can manage to communicate via MQTT protocol. Also, I think the this it's a lightweight implementation, so we needed to handle a lot of boards. You can see we have 5. In these 5 boards, we control 2 motors each, except one, because we have 9 panels. So one just controls one, but you know what I mean. And in this diagram, we take a look that we connect to the broker via the MQTT protocol, which is the one responsible to, again, managing the messages that are emitted and that the subscribers will receive. So in this case, you will see that the arrows are bidirectional because not only the boards emit a lot of information, but they do have to receive the signals from the server that allows them to move and to set the things we want to move. Um, Keep this in mind, right? And let's move to the other part. That's also the don't judge me thing I was mentioning. In the server, we not only do like all the processing for the interface web page, which are the CRUDs and interactions with the database and so on, but also we manage a lot of the heavy processing for the signals that we have to um, interpretate. So we have an algorithm that remember the input response file we generated? Okay, that generating of the input response file with this algorithm that's living in the server, but also many more. One of the others is, for example, this, that we make Schroeder integration, which you can think like, again, an inverse integral for this signal that give us the energy decay curve. Well, not only the energy decay curve, but all the 6 acoustic parameters that we are trying to put in our project. I'm going to tell you in a little bit these ones, but for the moment, save my words. We do this processing here, and we get the reverberation time, or RT, in general terms, of the room. And we also remember the scope of the project. We not only want to measure the existing one, but we want to modify it, because that's what the acoustic treatment means. We need to modify the acoustic data parameters that we can measure in the room. So for doing that, there's another thing, that's the Sabine equation, that give us the relation between the um, reflective values of a surface and the absorption values of the surface. So let's say we have a big reverberation time. So we need to add more absorptive surface in the room to reduce the reverberation time. And the opposite, if we have a small reverberation time and we want to make it bigger, we need to add reflective values, right? So with the Sabine equation, we process that to have a prediction about how many of our panels, because we already have the reflective and absorptive values, and we already have the area that each panel represents. It gives us the suggestion of how many panels we need to move to make these changes. So here, for example, in the part here, it says, for example, if it's in a position that's the reflective, being the reflecting phase 1, we have to move all of our phases to lower the reverberation time to an absorptive phase, right? Does that make sense? Let me see in the comments. So, is that like microservice architecture? Well, not indeed. Actually, no. The full response will be no, because microservice architecture will be, if we can make a zoom in this server, we will see that each part in the server, it's managing different levels of abstractions that could be moving one direction the panels or the other direction. I don't know, like handling the different REST calls to process the audio. If I have to do this in a microservice architecture right now, I will think of the full scope of the project. I will define services for audio processing, for panels movement, for database data retrieval, like in general things that already exist. For example, the swine sweep file, the volume of the room, another parameter that are like immutable. Um, and what else could be, for example, the treatment in general. Yeah, we will have to define many different services, and that will be living in the processing part, not only as a server, but yeah, a bunch of servers, right? But no, the answer is no. This is not microservice, because actually this is just a huge and immense service, and that's why I mentioned don't judge me, because yeah, I know that could be a good implementation, microservices. That's fine, but this not only it's just one service, but the real fact is that it should be at least two, because the server it's written in Node, and a lot of things are working in Node, but due to the processing of the signals, I had to do, and well, not I had, that was development of one of my colleagues. He had to develop that in Python. So the best thing will have to be have two servers separated, or at least the Python one living or being accessible through an API. But the real truth is that since my colleague didn't have that software engineering part that developed, uh, he had very well developed the signal processing parts. Uh, I like encapsulated his logic in having a Python file inside the Node.js project, and via Node system, yeah, I like run this file, catch the output, and write that output in this other file. Like not a good practice. I'm not accessing that through an API, but I'm running code inside another code, and that's not a good practice. That's all living in just one computer, right? Um, so yeah, that's not microservices. So things are interconnected and interdependent. It's that. Yeah, yeah, exactly. Uh, and you can think of. I think you mentioned the microservices because of these. There are many, and the broker, but actually the broker again, it's just responsible of managing the messages. Actually, I didn't write the broker. The broker was something that already existed, and we're going to take a look to the broker. There are many for MQTT projects, and that's it. But yeah, the systems are interconnected, so the interface depends on the server. Without it, it doesn't work, and database, server with the database, and so on and so on. But yeah, so this processing I just mentioned, these predictions, the all related to the acoustics, happen in Python, and I grabbed the Python code inside Node.js, and I made Node.js run directly on your computer the files, and you will see how I do it. Um, don't do it yourself. So again, it's not that a good practice, but hey, I was that pressure. Um, then we have a control strategy. This one, it's not even living in the server. These and each of the boards have this. This is an embedded control strategy that if you are not into control systems, don't worry, I will try to explain it as clear as I can. And the first part is that we define a trajectory, and that trajectory tells us which position should the motor describe, and in which time should that arrive. And we apply a control strategy that's not a regular PID, which is proportional, integral, and derivative to follow. If you don't know what a PID control is, don't worry. It's just like saying, okay, for example, there is the control P. Then it's if you're in I think this is well explained. Let me talk with you directly. For example, I remember my control classes assignments, and they explain it like this. Control theory was huge developed under the era of uh, what's that, missiles, yeah, well, with war, because they have to have precise control, precise and direct accuracy on where the missiles are going to land, right? So if for example, rocket to the moon, it's going one way, but you want it to be the other way, you apply forcing the opposite direction, and then the opposite, and then the opposite, and you get like this, right? Um, if you do it fine enough, you follow the trajectory. And if that doesn't make sense either, imagine you're riding a bike. If you're riding a bike and you know how to ride a bike, you take the control and you start riding, right? Um, you have to add more force to your legs if you feel you're falling down or you feel like you're going one direction. You need to turn the wheel the opposite direction and start riding that direction. Uh, the control systems are just that, being able to tell exactly the system what to do, not only not only what, but how to do it, right? Being very precise. Um, okay, I think, yeah. So what we did is we added that PID controller with one other strategy called the feed forward. So we add this feed forward for us to break the not moving state of the panels and put them in motion. And that's huge. It's complicated. I know it cannot sound complicated, but it is. So that's the control strategy we follow. And it looks something like this. Whereas the yellow line, the reference, I mean the trajectory you want to follow, and the position, the actually, well, this is a simulation, but it's how the system should respond, right? I think you don't have any questions this far. So finally, we have a model for the energy. You can think about this for the electronics. Um, Here we'll mention the components we have. We have these motors, which is just a DC motor with an encoder that allows us to measure the position. This is our, yeah, this is an incremental encoder. So that means we can start measuring the position each time it starts spinning, how many degrees, how many degrees it changes. Um, it has a gear motor attached, which is the one I mentioned, sorry, at the beginning, that it's just strong enough to move the panels. This is an H-bridge. If you don't know what an H-bridge is, it's just like a driver that allows to um, move the motor, giving pulse width modulation value, direction signals, and that said, it's, for example, the signal for the direction, it's just digital, 1 and 0, and the pulse width modulation value, it's from 0 to a threshold, how fast you want the motor to move. How that translates to, I don't know, RPMs or things like that, you have to do the maths of the values of your voltage, uh, and a lot of things that, don't worry for the moment, just trust me. If you go from 0 to 100, sorry, 255, from 0 to 1023, it means from low to speed, or even in not movement to all the movement. And finally, the processing, it's in these node MCUs. We already mentioned these, and I already showed you. Before I mentioned the things we had in mind in the beginning, we wanted to do with this with an industrial driver, which is very similar, very similar to the H bridges. Instead of 9 motors, one per panel, we wanted to use one big DC motor to move them all. I mentioned the problem we had. And instead of 5 node MCUs, we wanted to use one just Raspberry Pi. And obviously that wasn't needing an MQTT protocol. We just could connect via sockets, for example, or just directly API, REST API. We had to make these changes, so that's why we end up with these system. And it looks like this. This is the wiring diagram. Yep, I'm going to make this bigger. In the project, it looks like this. This is 1, 2, 3, 4, 5. Remember, because each one moves 2 motors, except of one that just moves 1. The connections in the physical world look like this for the ISP. The rest goes directly wiring to the H bridge, to the 2 funds. Well, the power supplies. There are 2 because we have a control stage and a power stage, right? So the big one goes for the motors, and the other one goes for the boards. And we also want to measure this, so we add a system or this little device to help us measure all the electric variables. Any questions this far? Hey folks, join late as it is 3 a.m. here. Can anyone help me know what it's being discussed till now? Yes, of course, and I think this is also helpful for the rest of your teammates. I'm presenting to you my thesis project, which I not built alone. I built it with 3 of my friends from the major. We present this on Monday. We had received great feedback from the judges and the evaluation board. I'm an engineer now officially, so I'm very proud to share this to you. And this is an IoT project. We'll be discussing not only the technical aspects, but what this project intends to do for you to understand fully. And don't worry, you can stay, watch the rest of the stream, and at the end, the recording will be available for you to watch the first part that you missed. Remember, this is part 1, and in this part 1, we are checking like all the code, all the technical aspects, and a lot of things. And for the part 2, I plan to give you a little taste of what this does. I cannot put the whole system in motion. You will see a video of it, but the whole system is just huge, immense. So I don't even have it in my home or in work where I am right now. I have it in other place, right? So I have a board with me that I will connect, and I will do like the same, but in a small version of it. But you will see the video again, and I will share to you the slides and the repositories and all, right? So that's it. Let's continue then. Okay, so let's see the interaction of the user with this, right? Um, this is how the UI looks like. We created this landing page just to show the all the information necessary of the system, like the connection status. This single connection status is the connection to the MQTT broker. These last treatment date and values are, remember, because we are trying to do acoustic treatments here, right? So for the user, it makes sense to see the latest successful treatment created, the values of reverberation time or RT of the initial, final, and desired, some values like the room volume and the date it was generated. These ones right here are the acoustic parameters I mentioned at the beginning and that we are calculating with the Scholler integral, right? Which is the early decay time, reverberation time 20, reverberation time 30, C50, C80, D, which is the, I cannot remember that, oh, that will kill me. But G, it's the strength of the sound, and some things like that. And the graphic shows the values per bandwidth. So these values changes. It depends on the bandwidth you are. And we mentioned we have a really wide bandwidth we want to check. It's starting from 155, sorry, 125 hertz and ending in 4000, right? And what's the value of this? Well, the end user will that it's an expert in audio will take these parameters and will say, oh, I need to modify these or add more surface in these and blah blah, right? So that's the home page. The next page it's about making the acoustic treatment indeed. So here the user just inputs the desired RT value that we want to achieve, and it makes, well, the system makes a prediction of the rest of the values that we will be seeing. Also, this start treatment button, it's going to orchestrate the whole system movement, and we will see the video of that. Then we have a history. Remember, we have a database, so it's just natural that we save these all the treatments that we do, and we have even a detail page that it's just as the things we saw on the home, right? The graphics, the values, and all, right? Um, sorry. And we have also a manual control page. In this manual control, the system does not only starts moving by itself and the automation part that we proposed, but you can give instructions to each panel, to each motor, to move degree by degree. You can give a set point, and the panel will move in that set point. There are a lot of information available here. For example, the status connection of the device. Remember here in the connection status header on top, we have the one from the interface to the broker. But are the motors connected to the broker? That we can check here on the motor uh, card. Yeah, card. 1, 2, 3, 4. Remember, we have 9 motors. What else? Well, remember of the control strategy we follow? We have in control theory we have things that are called gains. We have the integral gain, proportional gain, derivative gain. But since we are following feed-forward strategy for following the trajectory, we added a velocity gain and an acceleration gain. If this doesn't make sense, let me return to this and we will show that in the PID, this PID uses the first 3 gains, the P, I, and the D, proportional, integral, and derivative. And the feed forward that just says how we can help the PID to follow the trajectory. We add the velocity and the acceleration gains, right? Okay, let's continue. And let me see if you have any questions this far. Okay, no questions. So we said that, and finally, this is not for the end user, but this is really helpful for tuning the parameters. We saved a control graphic page. In this control graphic page, we can see the history of all the tunings that we have done, not for the acoustic treatment, but for each motor. So here we see a green line that it's the PMW output that the H-bridge is receiving, and in red and blue we have the set point value, the trajectory that we want to follow, and the input it's the described trajectory that the motor actually performed. We have a detail page of that separates the graphics, but we can see we have a very decent approach to what we want. Again, the red one, it's the desired trajectory, and the blue one, it's the one that's describing the system. The important thing here is not only that we reach the point we want to get, but how we do it. Again, control. Because if we stop the motion of the panel too, how to say it, too soon or too quick, we have um, we have a risk of harming the gear motors, and that happened to us. That happened to us like for now that well, yeah, at least 3 times. At least 3 times we had to change the gear motor, the gears. We had to even we even have a piece that broke out because the system has a lot of inertia, and if we just say to the motor stop suddenly, the panel keeps the inertia and it tries to keep moving, and that friction breaks a lot of things. So it's important that we accelerate easily, and we also decelerate also easy, right? This is called Bezier trajectory. So we managed to do that. What else? Well, let's then see the integration. That's our final system here. This is the CAD representation of it because we also did analysis of each individual piece. We integrated and we build it in the real world, right? At the end, we analyzed the results. We did run a bench test on the results, and we validate them with instruments that are used in real acoustic applications like a sonometer to measure that our system measures almost the same. I mean, we have some loss on the accuracy, but hey, we measure what very expensive equipment did, right? And the result tell us that indeed we managed to modify the acoustic of a room. We managed, and well, we validate that experimental and in theory. Don't worry about the theory validation. This is pure acoustics, and we don't want pure acoustics. Just think of the system as a system that worked, right? I just want to mention that. And now let's see the full movement of what's happening here. Remember, we start an acoustic treatment by giving the interface that button, and we'll see how that works. Just take a look to the video. Okay, okay. Let's see the video again. It has no audio, so don't worry. I know, and I will be pausing and explaining what's happening here. First, we start from the main page. We select the new treatment. We select the desired reverberation time that we want. In this case, we want to lower it, right? So we start the treatment, and the first thing that occurs is that the swine script file it's being recorded, played by the audio device, and the room again, it's reacting to that. If you can see it or can appreciate it, I don't know. Okay, I think it's not visible, but here, for example, it's the audio interface. We record with the microphone and the audio interface this response file. With the response and with the excitation file, we generate the impulse response, and that process passes on the server. We get the acoustic parameters, we get not only data, but the predictions of how many surface we want to change, and then we start the movement. If you see it, we do a little delay between the movement. First, the odd panels move, and then the rest move. So the prediction told us that we need to move almost all of the panels, except of the one in the middle, to more absorbent, to the absorbent surface, right? So remember at the beginning I mentioned we want to lower the reverberation depth, and again you don't have to worry about acoustics and everything, but the thing is, if we want to do that, we need to reduce the reflective surface, and that's what we did. So at the end, the last thing that happens, it's just that the system do the first process of playing the excitation file and recording and processing and that all over again to validate that the actual acoustic of the room changed, and that's it. That's the automation I'm talking of. So here I don't want to mention about the conclusions and stuff, but for us, not in how to say it, not in university and everything, but more like hacking and exploring, we want to care about the repo, right? So let's move to the repo. Repo, it's this one. Here you will see we created a lot of repositories that we end up not using, um, like the MATLAB scripts, Python scripts, first device that was for the Raspberry Pi, separate control just for doing that in Python and everything. But the ones that are important is device control. This is in Lua, which is the one we use for the Node MCUs, the server, the interface, and that's it. These three ones, right? So let me see if you have any questions. No? Else, let's start exploring them. I think it's worth seeing the first, that it's the server, because here is where all the magic happens, right? Uh, in part two, I would like to focus more on the device one, which is the ones for the Node MCU, because we will have the Node MCU to modify some things and play and blah blah blah. Right now, you watch the project, you saw already the whole scope of it, and here in the README, I is just showing the overview of how the MQTT map works. This acoustic control server is a system designed to control and monitor multiple motors using MQTT protocol. The server communicates with Node MCU devices that are connected to the motors, allowing for real-time telemetry and configuration. So, how MQTT works, if you haven't used it or heard of it, it's that it's a system that has a subscriber and emitters, right? So if you subscribe to a topic, you will receive the notifications each time that topic has a message. And if you emit, you will be emitting, sorry, to a topic. For example, we have the models, device ID, connections, the cleanup, the motor's ID, configuration, set point, telemetry, working, position, and logs for the errors. And we have a map that says, for example, the device ID are all the node MCU IDs from 1 to 9. Actually, this is wrong because there are only 5 of them. For example, for the cleanup, we send that from the server to the motor. The IDs, that goes from 1 to 9. The server at the motor goes, for example, the set point goes from the server to the motor. The telemetry and the logging of the errors, it's the opposite. They go from the motor, and these are the emitters, and the server and the UI in this case are the subscribers. Uh, in this case, it's living on Google Cloud, and the whole how to say that architecture describes Node.js project, but this is what I mentioned. We have the Python folder, and why we have that? Well, let me open the terminal. Let me see if you have any question. Could you share the link to the repo? Of course. Let me share the link not to this repo, but to all the repos. Okay, here you have it. Oh, also, before I forgot, give me a second, and I always forget to share the checking link. I'm so sorry. Don't kill me. Um, yeah, yeah. Here we have the checking link. Thank you. So, bands.mlich.io /events/12 74 8, and remember to check in to get your community points, right? So let's return. Oh, my node ends. Oh, no worries. Well, here in the Python, we created the virtual environment because this is also important, and we will see. And let's start from that. Okay, let's keep exploring the structure of the folders. We have the assets containing all the audio files that are required for the processing. Some of them are okay. I'm going to make this bigger. Yeah, I almost forgot to do that. So these audio files are important. For example, the strip sign never changes, but the ones that are the rest are generated through the code. Uh, some of them are saved in the database, not directly in the database, but in a bucket of, I think it was, what's the equivalent of EC2 in Google Cloud? Okay, I cannot remember, but they are saved, don't worry. These are just for having a temporary, how to say it, a temporary scope of it, and I added to the GitHub because I think that's not that odd to have them. Also, they are not that heavy, so I think GitHub can handle. We generate the response. we generate the impulse response, and we also have that for the second, the same response and the impulse response, but at the end, the final ones, the ones that we have after we uh, make the treatment, right? So then we can compare. Then we have the Python. We will reach this later. The env, GitHub app, example, package JSON, package log, README, and the server. The server mainly does this: creates the app required in the source app. It gets the config file for it being this, and it serves the application. Yeah, just like that. Uh, so let's open the source, and we have a config, which basically what it does is that it generates a model for the .env configuration. That's it. We have some contents, which are the MQTT topics. Again, this responds to the same that the ones in the. Oh my God, I'm not sharing. Sorry. I don't know why I stopped sharing. I'm sorry. I don't even know if that was a troll from my computer or even that was me doing that. Um, Let me return. It was a good thing I put attention here. Okay, yeah. I was mentioning about the assets file, the sweep sign, the one that we do have all the time: the response, the response final, the input response final. Do you want to hear how this sweep song sounds? I have to warn you, it's super annoying, so I'll try to reduce it as much as I can. So let me see if you let me see let me know if you hear this. Do you hear it? Okay. I hope that didn't annoy you. It goes from low frequencies to high frequencies, and that's enough. Um, for the response, it should be the same, but in this one, we get not the information from a synthetic one, but from how it sounds in the room. You see, it's like the recording of this, and the response, it's just like a very very small hit. You will see. For this one, I can. Oh no, this is the input response. You see that's it. This again, you will hit the boom, and that's it. That's how it sounds. Of course, not only it, but it has a lot of information that we'll be using for the processing. Huh. I was mentioning about the config. The config file just makes a model of the .env. I was mentioning the constants, and these topics are the same that we described here on the map, right? We are using them along of the code. So the models. Uh, we were skipping the error, the global configs, to put attention to these three. We have a model config, we have a treatment model, and a tuning model. These two are for the history that I mentioned here. For example, uh, the tuning one represents each of these, and the treatments represent each of these, right? The model config represents, there are only 9. These ones. We have the configuration for model 1, for model 2, for model 3, and that until model 9. So let's take a look to the description of the schemas in Mongo. We have the device ID and model ID. Remember, it is important to consider these separated because we could have a Node MCU board 01 that contains a motor ID 1 or 2 because each one can handle two motors. Remember that. We have the gains for P, for I, for D, for B, and for A. Remember, proportional, integral, derivative, velocity, and acceleration. The last value of the set point that was given, the phase ID that the current that's currently facing to the front, the last error, and a telemetry flag. Why is that a telemetry flag here? Well, we realized that having T telemetry sent each time, it was very high energy consuming. Sometimes the boards couldn't handle it. So we added as a flag for allowing it to be turned on and off. Last error, this is for the control system. Not all the times the positions were reached. The error was accumulated, so the next iteration, the next time, we will try to add to the set point given that last error, so the whole movement of the panel will be as it should be. Why is this? Imagine you want to move from one phase to another. So you want to keep a 120-degree movement. Remember, you have three phases, so there's the third of 360. You move it, but you realize you missed 2 degrees. That's fine, okay, don't worry. But the next time you want to move your phase to another phase, you will say another time 120. And again, you miss 2 degrees. So you have an accumulated error of 4 degrees. If you want to finally get to the first phase again, you move the other 120 degrees left. And at the end, you see that the whole movement it's misaligned. Why is that? Because the previous errors accumulated over the movement, and now you don't have an error of 1 degree or zero point 0.5 degrees. You have an error of 5 or 6 or even 10 degrees that are very, very visible. So that's why we accumulate this error, and we also have a way to clean this. But yeah, that's the main idea of why. So that's all for it. The treatment models, it stores the band of frequency, the early decay time, again the reverberation time, all the acoustic parameters, and this is the analysis schema. We also have the position schema that has an initial and a final as an array of the uh, 9 panels positions. The treatment schema in general has the room volume, an initial, a desired, and a final RT values, the response file after the treatment, the panel positions, which is the schema we checked before, the success, this is an input from the user, and some notes if you want to add it, and the analysis. That's the thing that we've covered first, the analysis schema, right? Finally, tuning model. It has the gain schema. So again, we have the K, I, D, B, and A. So imagine that you manage to have a good tune, but then you start modifying, start playing, and you cannot remember these 5 values. Don't worry, they're in the history. That's fine. We have the device ID, the model ID, who this tuning correspond, start time, finish time, the set point value that we're giving, the input, that's the array of the values for the trajectory, the output, that's the array of values that the motor described. This is given for the telemetry, so the boards are sending that information constantly. We handle them. I will show you how we handle them. The first models and the key gains. That's just the schema of the gains, right? So again, very simple. We have our models. Let's take a look to the routes. For the routes, we have the audio route. Again, we are skipping the error log global. The audio route, to be in concordance, we could call that the treatment routes, but hey, I just decided to call it the audio route. Let's take a look to the audio route. I think this is by far the most complicated one. But the thing is simple. We have express, route, path, file system, motor, because we are uploading audio files, the audio service. And let's see what we do. We have a base, that this base gets the latest success treatment. This is the one that uses the home. We have the get treatments. So this is the one that uses the history. The qualify, so after the end of the treatment, remember we display the information of the initial, of the final, and the desired to compare, blah, blah, blah. This is where we can add the messages and qualify the treatment as a good or as a bad one. So this is the qualify. The tune. And from this, I think it will be better we start from the bottom. First, we have a sweep sign, sorry. This sweep sign just gets from the audio service the audio file, and it sends back to be played by the speaker. Then, after we have played or sweep sign, we generate a response file. So that's why this is a post, because we are sending the information to be saved as the response audio WAP. And we get from that the values that are desired. This is where we start generating the treatment. And finally, since we are making this in many steps, we process it. We also have a response final, and why I separated this, again, I know that's not the best practice, but hey, for the moment, remember we're using different Python scripts that are not an API. That's complicated to explain, but it makes sense for me to have them independently. The response final and response just as it is says as the processing and as the processing final. For this, we received the treatment ID because now it belongs to an ID, and we start filling the information there. We checked first for processing. Remember that the excitation file exists, that the response file exists, or well, vice versa, and then we generate the treatment, and then we send the flag of that's already completed. Then, for the tune one, this tune makes the orchestration, because we now have the predictions, and this is where it all start happening. The panels move, the movement of the panels, basically. Yeah. So for this, I think it also will make sense not to keep exploring the server, but to show you on where this is on the interface and how that's processed step by step. Here, so this is the treatment page, remember. We define some values. So we have the room dimension. We use state, use effect, use raft, play and record buffer to warp. We also have audio services here for managing the playing and recording the audio. Some parameters, the treatment function, blah blah blah, and this estimate happens when we move the input. This is just making the animation and everything, but the real magic happens not here, but animate the bounce, clean parameter, from parameter function to handle audio processing. Yes, here. This is where the true magic happens. And again, I will explain the process the same as in the routes. We start the acoustic measurement. We call from the audio swine. This file URL it's played and record thanks to the functionality of the audio service we mentioned before here. Um, and we have the record buffer that then we send in a form data thanks to this in a blob format to the audio response to the store. And then after that's complete, we get treatment ID, we receive that treatment ID, and then we call for processing the audio with that treatment ID. After that it's complete, we set the initial and we send for the tuning request to audio tune, right? Same. Why I break down all this process and not just one single function, because there's a lot of things happening here. Again, uh, remember, just the first part, it's calling an audio file in internet. We receive that audio file. We play in a speaker. It could be one of the computer, but we use a separate speaker for that. Play the speaker sound, and at the same time record what's happening here in microphone. Um, Store that file, send it again as a buffer, reconstruct as a WAV file, process it with another flag, with another instruction, because we already save it in the database. We just call for processing it with the ID of the tuning, of the treatment. Then after that processing is done, call for the movement, and this also triggers another processing, which is again the prediction of how we can or what panels need to move. And finally, do the first two again. Call for the audio file of the wave, save our response, in this case now in our response final, and then now process it again for final and to compare. And final, just after all that's done, show the result model, and in the result model we call it qualify. Again, an orchestration of many services, of many things happening there. And even that, and with that, I haven't mentioned that in the tune that's here, for example, we call tune audio in the audio service, and this tune, 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 and this also calls the mother service to move. Well, yeah, I think in somewhere I'm calling here to the MQTT service. Oh no. Well, um, yeah, MQTT service to move. Well, the thing I want to say is just move the whole system, right? Um, so how are you going with the questions? Let me see. I think I hear nothing. I can hear you. Okay. I don't know which one of you listened to, but okay. Thanks for saying, even if you didn't hear me. I hope you can hear me now. Okay. Yeah, you say I hear. Yeah, you mean when I played the audios? Okay, no worries. I mean it's not important. It wasn't important. Yes, just about the audios. Yeah, sorry, I lost track of that. Maybe if I remove my headphones, but don't worry. It was an annoying sound that doesn't give us anything, and does not. It's important that we hear. It's important that we process, right? Uh, so returning here to the server, we were calling all about the audio services, right? I think that will be a great opportunity to talk then about the MQTT service. But first, I would like to move. Um, yeah, because the motor config it's simple. It's just like root for modifying some things. The tuning roots it's almost the same. Just getting them and showing them all. Like get the full list or get a specific one. It's okay, fine. But before we move to the MQTT service and the rest of the service, I think it's worth mentioning how to set up the MQTT, right? Um, for MQTT, we also have a utils connection for the Mongo, and in the service we have the MQTT service. So for the MQTT service, I also mentioned this like this. First, we connect to Mongo, then we bootstrap Express to use Course and Express. Then we set the MQTT service, and then we do things for mounting the routes. Controllers, so the controllers we have some handle not only connection to the DB, but publish to MQTT. So now it's worth seeing the setup, the MQTT service. Here, the MQTT service it starts with a function that's set up MQTT client. We pass the subscription topics from the constants we mentioned before. Uh, we have an initialized MQTT. This initialized MQTT parts from the idea that this comes from utils MQTT, right? So this already exists. Why I separated that? Well, because this is service and the other it's from utils. I don't know if that makes sense. At the moment, I think it makes sense to me. But yeah, here on the MQTT util, same as in the DB ones, we have some configurations needed. We need a broker, a URL, somewhere to connect to, a client ID. If we don't pass this, I think this is generated dynamically, but I wanted a specific one. It depends also in the broker we're connecting. Some of them require a username and the password. I think the one I use, I end up setting it to not use it. But hey, I forgot to remove this. Then MQTT comes from a library. That's MQTT. Simple as that. So we say MQTT connect because we export the function. And on that, if you put attention here, we receive as a callback function a thing that's on message. We can call this as we want. Remember, don't worry, this is a callback function. But we are executing that callback function every time we receive a message. Because once we connect, we have a client. And that client has methods to listen to some things, to a connection, for example, or a disconnection, a message, and that's it. The client lives locally or in the base scope of this file, so that's why we also have a publish in MQTT and a subscribe in MQTT, right? So we export these three: init, publish, and subscribe. I think the reason why I did this is because this is agnostic to doesn't matter where we're using this. This is the base configuration for MQTT in all cases, right? So now in the service that it's explicitly for this use case, we want to initialize that. And the callback function we're passing is that every time you receive a message, you are going to say, hey, sorry, you have a message, the topic is this, and the message is that. And from the topic, we receive some things that are very important: device, motor, category, and subcategory. And this comes from the parts. Why I know that? Because we define that here. Remember, if the first it's motors, it doesn't matter to have the motors here. Then it's device ID. Then it's the motor ID, the category, config, telemetry, or logs, and subcategory. So we process that message depending on the category. The first category, it says, if the category is telemetry, and if the subcategory is working, you will handle the working status. Else, if the subcategory is position, we will handle the position data. Here I mentioned some things, blah, blah, blah. You can read it at your time. But the thing is that we are managing the working status. How we manage that? Well, we find the motor configuration for that device. If that configuration exists, then we parse it to a JSON. And if that's a busy status, then we create a new tuning. And if that it's not a busy status, but a ready status, we finish the tuning that we already created. In the position, we do kind of the same. So we expect, because we set up this way, and again, this is, again, I separated because this works for all QTT implementations, and this works for my specific MQTT implementation, which I define the topics, and I define the topic structure to fit this device, motor, category, and subcategory. The handles of the messages, it's through a processing message function that divides and relates depending on the category and the subcategories. The handle and well, the handle for working status and the position works this way. First, we receive a first flag of the working to start a new tuning to save on database. Then we received all the position data to fill and to feed that first tuning we generated. And at the end, we received another handle working status that it's like complete, that finishes like the filling of the positional data. So first layer, we receive a working status. We start filling that working status with all the data, and we set the last working status to done or busy. I can remember. To set like, okay, stop filling that data. You are going not to receive anything more. And that's how this works. Again, if we receive the busy, we start it. If we receive the ready, we finish it. And in the meantime, you pause sorry, you add all the information for the input, for the input and the output to the active tuning currently, and that's it. So I hope that makes sense, and that's translated into having this control graphics, right? Uh, Let me see if you have any questions. Okay, no questions this far. Let's continue. Um, hmm. Okay, what else we have besides the handle position and the handle working? We have the handle error and the publish motor setup config. When did it happen? Publish motor setup happens uh, in the orchestrate tuning, and well, yeah, motor MQTT and the audio service. No, in the oh yeah, oh yeah, we use the orchestrate tuning function here in the audio service. Yes. Um, yeah, I was mentioned. For example, when we call the tune audio in the routes, I think we didn't cover the audio service, right? We will do that really simple and really quick. So when we call the audio service for the audio route, we basically want to interact sometimes with the database, like in this one, get audio file, get latest success treatment, get all treatments, get the final response, blah blah blah, right? But there are some of them, like this one, that does the grouping I mentioned before. Verify Python environment, for example, what it does, it's encapsulate with promises, and Python spawn, it's for managing threads in JavaScript. Well, in Node.js, which is JavaScript. We create a new thread for checking the Python version and if it works. Once that process closes, and if it closes not with an error, what it does is that it resolves depending on the inputs. We spawn even inside these order. So again, we are using threads. Um, we do an import of the we do an import of the libraries we need in Python. Uh, if the process data does well, it results in a success, and it doesn't compromise the rest, right? This is just, again, as mentioned, as the name says, verifies the Python environment. Why this is important? Because in Rust, we need to verify the Python environment. For example, for processing the final audio or processing just the audio, we first verify the Python environment. We checked if the script exists. We execute the activation of the environment, and when the environment is active, we execute Python with the script we want, and we pass the parameters for the function that we want to execute. So again, we collect the data from that running the script, and when that closes, we get a parsing of the result data that was collected. Uh, Data to string. Every time this standard output gives an output, that means every time Python prints, that can be simple as that to explain. We save that whole processing standard output, and when that closes, we have to parse that into a JSON. And finally, for this processing, we get the RT, or reverberation time 60. That's it. For example, for the tuning of the audio, we do kind of the same. We call the Python script for that. We initiate the environment. We call the script for tuning. For that processing, we pass the volume of the room, the reverberation time, the desired reverberation time, and the position of the current motors, and we get that from the motor configs. Um, Again, we wait for all the prints of Python in this time. We parse it to be a JSON, and finally, um, we call the orchestrate tuning with the current panel position and new panel position, and we pass the all motor configs, right? So this is where we're calling the MQTT service with the current panel positions, the new panel position, and the existing motor configs. Why is that? Well, we first verify that both have the array. We verify that the array are the same, and we start modifying this. We define a delay for the movement between one and another. We have a helper function to process this by parity if there is odd or if there is even. Um, if there is odd, we manage to move the panels one and then the others. Um, and well, looking like this, we set a motor configuration and we publish that motor configuration. So now the motors will receive in the MQTT terms the instructions, right? So we wait for them to move, and we checked. I added another uh, delay here. In the video, you just watch that all the odd ones move at the same time and all the evens at the same time. Here, I added another delay, which is start moving the first odd, then after I don't know how many seconds I add, then the other, then the other, then the other. So it looks like a cartoon now. First you move one, then the second odd, the third odd, the fourth odd, then the first even, then the second even, then the third even, and finally the last even, and that's it. Uh, I had a lot of commented code here because again I was running out of time, but we managed to complete it. And we said thanks to the helper function, process all the panels by parity true because we have first even and then odd. Um, all right, at the other side, first odd, then even. Finally, we complete all the movement, and that will be it, right? So we have the orchestrate tuning, we have the publish motor config, and this used for the orchestrate tuning. It receives just the motor config, and it sends the information to each panel or each motor respectively using the topic, right? And the publish MQTT, which receives the topic, the specific payload we want to send, and MQTT has this QoS, I think it's quality of service, that just basically says from 0 to 1, if you really really want the device to receive the message being 0, like okay, you send it, I don't care if the subscribers receive the message. One, it gives a little bit more quality, and two, it's for sure the receivers will receive the message. And when you subscribe, it's like the same. You can subscribe with a quality of service and as a scale of 0, 1, and 2. Uh, okay, right, perfect. The function for the publish MQTT, it's the one we saw here on the MQTT. Yes, it's this one. Remember, we also have one for subscribe, but we're not using that here. So we have another one for getting device ID, for getting the motor ID, the config, the calculate optimal rotation. That's another helper function that I added. But the ones using here that we export, it's the setup, the publish, and the orchestrate, right? And the orchestrate, remember, it's being used here on the tune audio. Um, the qualify and the frequency analysis. Qualify it's simple. It also calls just an REST API, and the frequency analysis it calls also Python. So you will see at the top all the Python scripts we're using. First, we have the audio file direction, the Python script for the rear analysis, for the tuning, for the frequency analysis, the one for the virtual environment for verifying that. So basically, three main Python files for doing the processing and all the analysis. So, uh, 10 minutes left. I would like to see if you have any question this far. Remember, this part one was beautiful for introducing you to the scope of the project, what we wanted to do, how we do it actually, the results of it, gives you the whole and full structure of the project. And at the end, we start seeing the magic in how that happened, right? The code of how we process the signals, how we send the instructions, how we connect via MQTT, and the server that interacts with that. Um, Remember, we will be having part two at the end of the day. Well, for me, that will be at the end of the day. Probably for you, that will be the tomorrow. um, Thanks for joining. If you have any questions, please let me hear in the comments, and I will start spoiling you to what's happening in part two. In the part two, we are going to take a look not only to the rest of the code on the server and the interface, but with the Lua, and we are start checking why I choose these words. Why Lua? Because probably it's the first time you heard about this programming language. Um, yeah, I see one comment here. It is my first time in IoT, so kind of overwhelming but interesting. Hey, don't worry, don't feel overwhelming. Yes, I know this is not a basic introduction, but here in the global hub, we will having some basic introductions. You probably can look for them, and I'm going to take advantage of that to um, spoil you. I think that's already announced, but we will be having Beginners Week. So remember, each time the Majorly Hacking starts a new season, we have the Beginners Week. That's this second semester of the year and at the start of the year. And in the Beginners Week, you will have the chance to learn a lot of new things, right? Like IoT. I'm really sure some of my colleagues are going to give some IoT starters. If not, why not? I can do it. But yeah, don't worry. This is just a little taste of what you can do in a real world scenario, in a immense scope, in a very ambitious, I would say. I don't want to sound like I am doing magic, but I kind of feel proud of what we achieved. Unfortunately, it will be 4 a.m. for me, part two, so I won't watch it, but awesome presentation. I really like the project. Hey, thanks to you. And don't worry, you can watch the recording if you want, and thanks for joining. This will post on YouTube? Yes, for sure. If you head to globalhackweek.mlh.io, which is the link I just shared, you can find the link also to our YouTube channel where you can find the recordings. Yeah, I also feel overwhelmed, but mostly because of the handling sound thing. Although the code it's mainly intuitive, I think. Hey, thanks. I try to do as intuitive, and I try to document a lot of things there. Um, you can take a look close and tell me what you think later. And well, yeah, I know you're absolutely right. The audio processing and the handling sound there is one of the most challenging parts because it's out of our scope, right? It's out of our engineering part, at least as software developers or at least as computational science, right? Um, That will be great. I did your register for Beginners Week. Hope to see you there soon. Yeah, a lot goes into this, but it wasn't contracted alone. Yes, yes, of course. I have to say this is not the work of just one person. We were four of us. Um, a lot of mm, how to say it? Yeah, a lot of hands are required to build these kind of systems. So yeah, you're right. Uh, that's why we always want to encourage you to be a team players and to do your best effort there. So we're running out of time. I hope to see you for part two. If you can watch it live, remember to watch it on stream, like the recording of it. So it was my pleasure. Thank you so much for joining, and I hope to see you soon. And I don't say goodbye, I say see you later.